Okay, so I'll give you a little bit more information about that whole situation. Here we are tramping along the jungle floor with our old-fashioned bore-sighted musket. Bore-sighted musket, no range correction.
What is he doing?
He is filming the back of your head.
Why? Because he flies.
He's going to be working on a project that involves taping various things in and around the class. So just do what you would normally do, or in some cases.
Hello.
In some cases, I guess I shouldn't say do what you normally do. In some cases, I should say you maybe do a little better than you normally do.
Can I say that Monica's head is hollow?
It takes one to know one.
Spectral Man here.
How many people are living in there? Please.
I can take my hair. So much.
Yeah. You guys don't need much of a distraction. You realize that this class is the farthest behind of all three classes. The farthest behind of all three classes because of stuff like rising backwards.
It's a lot.
Let's see if we can do this in some kind of academic way. Old-fashioned bore-sighted musket, and the problem, as you may recall yesterday, was highly contrived. The monkey loses his grip on the tree, doesn't push down, he simply lets go at the same instant that the bullet leaves the musket barrel. And the question is, will he still be hit, or will we have a miss because of the influence of gravity? Now, I know that a lot of you have opinions on this matter, but any opinions that you might have must be defensible. You have to have a good defense, and what I think we'll do is have you restrain yourselves from expressing your opinion for a while, and we'll look at the defense first. And by the time we get finished, you'll see that we have much more defense than probably any of you really imagined. In fact, I need to warn you a little bit. In fact, especially in this class, we're going to need to be careful with this. By the time we finish, we're going to have this whole chalkboard filled, and you'll be able to take them home, and they will be very impressed. They'll think, boy, this is like the university already. If you would like to not copy them down, you'll be happy to know that you already have them in your possession because I handed them out to you on a sheet yesterday.
Thank you.
So that depends if you want to impress the people at home or not. I had one guy in my third grade class that said that he would just take his pencil and go over all the ones on the sheet, and that would look like he wrote it, and he could show that.
Ian wants to know what you shoot. Not only that, but do you have an extra sheet?
Yeah, I'll give you one right at the end, but not up here right now. I talked to you about that yesterday, so you should be kind of used to it by now. Imagine I had a little foot switch down here. I could flip and we could temporarily turn off gravity. If we really turned off gravity, of course, we couldn't do the experiment at all because none of us would even be here to do it. But let's imagine we've got this set up and we can turn off gravity. What would the path of the ball be? Straight line. So if I aim correctly at it to begin with, you get a hit. Okay, so we have gravity turned off. The musket has a certain muzzle velocity of which it is capable of, and that's a fairly fixed kind of thing. It's not infinite. And so I can draw a velocity vector, z0, to represent that. It will be fruitful for us to resolve that velocity vector into a couple of components. So there's the x component, and there's the y component. I'll call that one v0y and v0x. It should be evident to you that v0x equals v0 times the cosine of the angle. The angle here is the angle of elevation of the gun barrel. So that's also something that we presumably know. Those things are all known. And v0y is v0 sine of the angle. All right, so let's see what happens without gravity. Without gravity, the monkey lets go but stays there, and the bullet travels in a straight line. Is there any acceleration involved?
No.
No acceleration in either direction. So we have uniform motion in either direction. In the x direction, I have dx, that's the velocity in the x direction at all times, is the same as what it was initially. Notice the subscripts and the way we're describing initially versus later. And that means it'll be v0 cosine the angle. In the y direction, the velocity doesn't change there either. v0 times the sine of the angle. The x coordinate, which I'll later on be referring to distance downrange. The x distance, x direction will be called the range now. Well, anybody know how that works in uniform motion? If there's no acceleration, distance equals rate times time. Rate is distance over time. Distance is rate times time, so I'll have dx times the time, or v0t times the cosine of the angle. Why did I put the t up there and not back there? Some of you that have
Because you're gonna get the cosine of the cosine t and not the cosine of the v
it
times
is,
t.
that's it. I don't want that to look like cosine of theta t. So I could fix that by putting parentheses, or I could fix it easier just by moving the t out of the way, and it saves me having to write parentheses. Why? Carlos is not here today. He's normally here, but he's not here today.
He's ditchy.
You did, yeah.
Because I was supposed to do
Second lunch?
Oh, that dude?
Yeah.
I still
Well, yeah, right here.
Oh, Spectral radiator. Spectral MC Hammer Power 1.
Right here. Turn it on.
Okay. Since I wrote the x one for you, and since we know that there's no acceleration in each direction, tell me what the y one is.
Y equals b.
VXT.
Y equals b. Y t.
VOT.
B o.
times sine
Theta.
Okay. And we are now done. For the case where there's no gravity. If I want to know something about the motion of this musket ball right now, all I have to do is tell you what time to put in. You'll say, well, when do you want to know? At what point in the flight do you want to know? So I'll say, well, I want to know 3.9 seconds into the flight. So you say, okay, and you go over here and you put in 3.9 seconds wherever you need to. And those are assumed known ahead of time here. We know the most velocity gun, we know the angle of the line. So those are constants for our purposes now. Cancel out, you know where they are. So just put in the values.
Usually we have a value.
Right now, if you told us 3.9 seconds, we're good because you didn't tell us.
Yeah, we're assuming that this stuff in this section is all known. Know the angle is given. Know the angle, you know the most velocity. You either have a way of measuring it or you know what it is going to be. Okay, now, of course, we've got to turn gravity back on. Does gravity have on those x equations?
None on the X.
None on the x. Gravity influences only the y equations because gravity acts this way. We're only looking right now at the x motion. So that means the two x equations I can rewrite the same as they are over here. So in the x direction, nothing has changed. Vx, v0, cosine of the angle. The x coordinate will be down here, v0 times the elapsed time times the cosine of the angle of launch. Now, the y direction, we are going to have something happen. Gravity, as this musket ball gains altitude, what is the effect of gravity going to be? It'll be decreasing its y speed, won't it?
Yes.
Decreasing the y velocity.
It'll be decreasing the y velocity. And we've got to figure out by what amount does it decrease the y velocity. Well, it's going to decrease the y velocity 9.8 meters per second squared for each second that the thing is in the air. If I multiply the acceleration by the time, that tells me the velocity achieved after that amount of time. I'll have to use that as a correction against what we already have. So v0 sine of the angle minus 9.8 meters per second squared times the amount of time the thing is in the air. You may remember where this little thing came from. Down here parenthetically, I'll make a comment. V final equals acceleration times the time. That's where that came from. What we're saying is that it will gain altitude at a rate equal to the rate it would have gained altitude without gravity, minus the influence that gravity has on it. This factor, this term here is a constant, but this one is variable. As time goes on, as our stopwatch ticks along, this thing keeps growing. Eventually, this second term will get to be as large as the first term, which will make Vy equal to 0. And at what point in the path is that? At what point of the flight?
When it stops.
When it hits the ground?
Oh, wait, we stop. Why velocity is 0? When it goes up.
Something like this. Let's suppose for the moment we miss the monkey and it misses the tree and ends up, we'll assume that it starts and stops at equal height. It doesn't look like it on that drawing. At the top of the path, the highest point, right here, it ceases to gain altitude anymore and it begins to lose altitude. So right there at the apex of that path, the y velocity for an instant goes to 0. It actually passes right through 0. It doesn't stay there, but it passes right through. If I wanted to, for example, I could put a 0 in here and solve this for t. And that would tell me how long it took to get to the top of the path. Tell me that first half of the flight time. Okay, let's do the y coordinate. The y coordinate itself, v0t times the sine of the angle of launch. That's the height it would have reached if there wasn't any gravity. Let's say we look at it at this instant. Without gravity, it would get to that point. With gravity, it gets to this point instead. What can you tell me about that distance?
Minus 9.
Well, let's see. What was our little equation for distance under uniformly accelerated conditions? D was
Equals RT.
Galileo's experiment. We first encountered that. 1/2.
1/2 t squared.
A t squared. But now what's a in this case? G. Okay. In other words, we can say it like this. The ball will reach an altitude that is equal to the altitude it would have reached without gravity minus the distance it would fall in that amount of time. If I shoot this musket ball and simultaneously drop an identical ball, this distance will be the same as the distance the dropped ball would travel in that same amount of time, because gravity is influencing both of them exactly the same way. You remember the little experiment we did with the spring launcher over here? One was projected sideways and the other one just dropped. Gravity influenced them both the same way. So the ball will reach a height that is equal to the height it would have reached without gravity, minus the distance it falls because of gravity in that same time. The distance it falls because of gravity in that time is the 1/2 gt squared, and the distance it would have reached in that time without gravity is the v0t sine theta. So we're using gravity as a correction. Launcher. Now we've arrived at the same point today with a more general case where we've got this angle involved. If I want to know anything about the motion of the projectile here, v0 times t times the cosine v0 squared over g times 2 sine of the angle, cosine of the angle. Some of you probably will have little light bulbs blinking off and on in the back of your mind. You see that. Carlos, actually you're all whispered it in your ear back here when nobody was looking.
Yeah.
That's a big one.
Right now, let's look at the turn red now.
Right, where did the cosine
Be quiet.
This is a little trig identity that you learn in trigonometry 2, sine x cos x equals sine of 2x. You had to prove it in that class unless you're not in trig.